Let's start. Friction. In theory, this should all be review from Physics 11, but some of you didn't have me last year, so I'll basically be teaching this from scratch. You okay, Sarah? You know there's a little electric one to your left there, too, you could use to sharpen your pencil, but whatever works for you is good. What is friction? Friction is due to the interlocking of molecular hills and valleys between a surface and an object on that surface. Even for surfaces that appear smooth, like your lab tables, for example, if you zoom in on the atomic scale, they are rough. And so when objects slide across each other, those molecular hills and valleys grab onto each other and they resist or impede sliding. In terms of a direction, it's always going to be in the opposite direction that the object that we're looking at is trying to slide. That means that friction can resist motion, like when you're trying to slide, say, a table across the floor, but it can also create motion for walking or rolling. Example 1 says, draw the direction of friction in each case. These were typed, I think I may have told you, these notes were originally typed by a friend of mine in Word 1995 for Mac. And so they're starting to show their age. There should not be any daylight between this desk and the floor. This should actually be sitting, this block in the floor should be sitting like right there, just for the record. So let's imagine we're sliding a block to the right. Which way would friction be pointing in this situation? And in this case, friction would be resisting the motion. But friction can also create the motion. For a car speeding up, we talked about this last year, right where the tires meet the road, the tires are pushing backwards. Forces come in. So that means there must be a force on the tire pushing forwards. What force is that? Keegan. Friction. This is why cars can't drive on ice. It's not that there's some engine force that pushes a car forwards. If all you needed was the engine, cars could drive fine on ice. What's missing on ice? Friction. And so friction would be acting forwards. In fact, in my free body diagram for a car accelerating, that's the free body diagram for a car accelerating. I think I told you the story last year. I was at a conference and there was a person teaching physics out of their comfort area. They'd been given physics and they weren't that comfy with it. And they had, don't write this down because this is awful, they had F engine and then they had done friction like that. No. Friction isn't what's slowing the car down. Again, if all you needed was the engine to get the car to drive properly, then you could drive on ice. This is your free body diagram for a car. If we're being more realistic, we could add air resistance, but have we basically been ignoring air resistance unless the question says? Yeah. What about for a car slowing down? When you tap on the brakes, what really happens is your tires apply a force forwards on the pavement. Forces come in. You're going to get a force backwards from the pavement. What force is that, Madison? Yes. In fact, the free body diagram for a car coming to a stop is almost identical for the free body diagram for a car speeding up. You still have gravity and normal force, but in this case, friction is removing motion, reducing motion, not creating motion. This was one of those free body diagrams last year that was so easy that it's tough. I gave you a bunch of questions. I think there was one, a dragster speeding. In fact, I think there's going to be one similar in the homework here as well, where, okay, if it's a dragster speeding up, that's your free body diagram. By the way, in this free body diagram, who's winning? Friction. Who's losing? It's a trick question. No one. You would just have friction equals ma. And same here, friction equals ma. What does friction depend on? We talked about this last year, and we said friction depends on two things. The first is how sticky or slippery two surfaces are in relation to each other. That explains the difference between trying to walk on ice and trying to walk on gravel and trying to walk on pavement and trying to walk on wet grass. All of those are slightly different because they have a different level of stickiness. Who remembers what phrase we used to refer to this level of stickiness? It was the something of something. We called it the coefficient of friction, and it was represented by the Greek letter mu. That one there. Oh, I even have my mu right here. It was represented by this, right? What were the units for the coefficient of friction? It doesn't have any. It's just a ratio. So it is not a force. It's not in newtons. It won't actually show up in your free body diagram in your arrows, but it's used to calculate friction. The closer mu is to 1, the stickier the object is. The closer it is to 0, the slipperier an object is. Was that somebody knocking at the door? Oh, we got somebody at the door there. Absolutely. You got my friend. So steel on ice would have a coefficient of friction. We'd probably pretend it was 0. Typically, when we're talking about ice, we'll pretend it's perfectly frictionless, even though all of you have walked on ice enough to know you will eventually come to a stop. There's a tiny bit of friction there, but not much. Bigger than 1 would behave like glue. It would be, it's stuck, and I have to apply a larger than normal force to get it to get loose. Or if you're trying to pick it up, you would say, I have to apply a bigger force than mg to break it loose. Glue is a little bit weird, though. It's not actually technically friction, so I'm not going to talk about that. But as a good analog, you can think bigger than 1, really sticky, right? What was the second thing that friction depended on? The normal force. Put my pen down somewhere dumb. I was like, what? The normal force. Because that allowed us to explain, first of all, if nothing's touching it, the normal force is mg. Heavier objects have more friction. You got to push harder to overcome friction. But Lena, that also allowed us to explain why when you lift up on something, friction gets smaller. When you push down on something, friction gets bigger. So we said that friction depends on mu, the coefficient of friction, and the normal force. And in fact, the box down here, most of you probably memorized this one from last year, but we said that friction was mu times the normal force. The normal force we'll figure out from the free body diagram, and then mu will tell us. And then example 2 says this: consider the block below, which is being pulled by student 1 across a rough surface, include friction. Ooh, key phrase, constant speed. And I think what I told you last year was, instead of pulling a block, let's imagine the benches at the back of the gym that you slide around to get them out of the way. I'm guessing most of you have pushed on those benches at least once, except maybe for our new students, but most of you at least once or twice have slid those benches around. So let's suppose, just for Clody, you're pushing a bench along at a constant speed. Okay? Student number 2 pushes down on the bench with a force F. Let's say, I don't know, Zaina comes along and she decides she's going to sit on the bench while you're pushing it. That'll be our downward push with a force F. Okay? Assuming you don't change your pushing force, the applied force stays constant. What happens to A, the weight, B, the normal force, C, friction, and D, the motion? Let's see if we can walk through this. Let's put the letter A right there. When I say weight, when I say weight, which force am I talking about? Okay, so weight is mg, right? That is, when Zaina sits on the bench, Chloe, does the mass of the bench itself change? No. Does gravity change? No. So does the weight change? Okay. What does change? You know what? We should do a free body diagram. In fact, we should finish this diagram right here. Here is the mass after Zaina is sitting on the bench. Zaina, what are the forces acting on this? Get the obvious one. And it would be the same mg as before, so I'll eyeball it, try and make it the same length-ish. We still have F applied. This extra push, what force has that affected? What other force am I going to put on here now, Zaina? And your hint is it sinking into the ground like quicksand? Is it flying here like Superman? So, bigger, smaller, or the same size as mg? I'll give you a hint. It can't be the same size. Why? Is it sinking into the ground like quicksand? That means the normal force is resisting both of those forces. So the normal force, I'll really exaggerate it so it's obvious, would be much bigger. If we're being really, really fussy, it would be the mg of the bench and then the mg of you. That's what the normal force has to be. Okay? If another person jumped on, now it would be the mg of the bench, the mg of you, and the mg of the other person. Okay. If the normal force gets bigger, what other force gets bigger? Friction. And I'm pretty sure that probably, because I've seen kids jump on the bench when their friend is pushing it, and I'm guessing all of you have seen that at least once, I'm pretty sure friction's bigger than the pushing force. So, Zaina, what's B asking? What happened to the normal force? Bigger, smaller, or stayed the same? I'm going to write this. F, N, and my abbreviation for increased is an arrow pointing up. You know what my abbreviation for decreased is? An arrow pointing left. Oh, down! That's much better. Let's do that. That makes way more sense. Down. Sure. What happens to friction then? Well, if friction is mu times the normal force, and if the normal force got bigger, what happened to the force of friction? It also... That's why I drew this arrow longer than this one. And so what's going to happen to the motion of the block? Claudie, if you look at this, how will this block accelerate? Which way? The obvious. Left. It was moving to the right because you were pulling or pushing it. It's going to accelerate to the left. It means it's going to slow down and rapidly come to a stop. Will it suddenly start moving backwards? No, friction is a weird force, especially static friction. Once it comes to rest, static friction is only as big as it needs to be to cancel out someone else trying to move it. So as soon as it came to a stop, if you were pulling with 150 newtons, friction would be 150 newtons. If you pulled harder with 175 newtons, you know how big friction would be? 175. Okay? If the maximum friction could be was 200, and you pull with 201, now it'll be unbalanced. You'll have 1 newton of unbalanced force. 201 to the right, 200 to the left, your net force is 1. Okay? It says explain your answer using principles of physics. I think we just did there. I'm not going to be too fussy on that. Ooh! We can vote on example 3, though. This is a good one. A student gives an old shopping cart a big push on a flat, rough surface. Which of the following is the best free body diagram for the cart after the student has released it? Let me pause the video for a second. Who says, Mr. Dewick, easy? It's diagram A. It's going to be A, Mr. Dewick, A. I got 1, 2, 3. I got 4, 5. Oh, I got a 6, 7, 8, 9, 10, 11. I got 12, 13, 14, 15, 16, 17, 18. Oh, Zaina jumped in. Why is it A? First of all, what's wrong with D? How would D be behaving if that was correct? Which way would it have to be accelerating? That would be speeding up. So it can't be that because I noticed it did not speed up. What's wrong with C? How would C behave in terms of its acceleration if all the forces were balanced? It would keep going in a straight line at a steady speed like in outer space. I think it was slowing down. Yes? Why is B incorrect? Well, this one's a bit trickier. Either the forces are meant to be balanced and it's like C, or it almost looks like this arrow is a little longer than that arrow. If anything, it's going to be speeding up. Jan, was it speeding up? What's the correct answer? What law did I use to figure that out? The idea that if I'm slowing down, there has to be an unbalanced force pointing to the left. So the fact that someone said third means we don't know which law. If you knew which law, you could write down the law and just drop the mic and walk off, and I'd be fine with that. But since we don't know which one, we'll actually have to express the law. We'll actually have to say only A has an unbalanced force to slow it down. Newton's first was the one that you were looking for. That's the one that explains why objects do or don't accelerate. Newton's first, the law of inertia. And if you had said Newton's first and walked away, I give you full credit for that. But I also did tell you last year, you don't need to memorize which one is which one is which one. You need to know what they are, though, so that you can at least understand how they work. Okay. Example 5 says, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know what? I'm going to do these simultaneously. I'm just going to draw a line down the middle of the page. Did that work? No. Let's try that again. There we go. Pretty straight. It's just the mouse and held the pen in one place. No? Okay. Okay. Mallory, what does A want me to find? Did you say equation? You know what? Before I even start, you know what this might be a good job for, Mallory? I'm going to do a free body diagram. Oh, did they give me a picture? I'm going to wimp out and label the picture. All right? Mallory, what are the forces acting on the left-hand one? Get the obvious one. I totally agree. I'll call that mg. What else? Sorry? Don't go there yet. We want to go systematic. Usually, okay, after gravity, what I usually do is ask, does it need to be canceled out? Right? So that's why I usually move to normal force next, because gravity's fresh in my mind. Is it sinking into the ground like quicksand? Is it flying through like Superman? Normal force bigger, smaller, or the same size as mg? So let's eyeball it. And then I heard you say applied force. I agree. What else? Which way? Yep. Bigger, smaller, or the same size as F applied? I'm going to guess smaller. I'll find out that I guessed wrong if I get a negative acceleration. Then I probably picked the wrong winner, but I'll tweak it really, really quickly. For now, I'm going to go yoink. Okay. Sarah, let's do the right-hand diagram. What are the forces acting on it? Get the obvious one. I totally agree. What else? Is the normal force bigger, smaller, or the same size as mg? And how do I know? It is bigger because it's canceling out mg, but what else is it also canceling out? The 15. So I'll exaggerate it so it really catches my eye, so it's obvious that something weird's going on. What else? Yeah, I would probably take care of the 20 next. What do we call the 20? F applied. And then, you're right, I would add friction. Okay. Now we're better. We can handle this. We can do this. Nick, what does A want me to find? Okay, I'm going to do them both at the same time. So let's put an A there and an A there. In the first diagram, when they say vertical force equation, here's what I think. Are we sinking into the ground like quicksand? Are we flying like Superman? So can you write me a vertical force equation? I think the forces are, I'm looking for a word that starts letter B. Yeah, and really what we're saying is everything down has to equal everything. And if I was going to write that, what is everything down in that first diagram? There's only one arrow pointing down. Which one? What's everything up in that first diagram? There's only one. So as an equation, I would say this. Okay. What about in the second diagram, the right-hand one? Are we sinking into the ground like quicksand? Are we flying into like Superman? We are? The question doesn't suggest we are. So I'm going to assume that everything down equals everything. What's everything down? There's two things.
No idea what you're saying. I hardly understand you.
What? There's something else pointing down. Yeah. Say it loud and proud, the two of them. And? What would I write instead of the word and mathematically? Yeah. Everything down has to equal everything up. There's my vertical force equation here. You okay with that? Okay. Keegan, what's B want me to find? Friction is what times what? Just read the equation. Friction is what times what? We put it in a box or it's on your formula sheet. Mu times the normal force. Yeah. Well, let's keep going. Keegan, what's mu? I don't know. What's mu with you? What's mu? How'd you get that? You're right. Can you be, just for our viewers on you, how did you, where are you looking? Right there. It's on the, I'm looking for that starts with the letter D and rhymes with iagram. It's on the diagram? Good. So 0.12. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. What? Yeah. And I've got to be careful. You'll never hear me say, oh, the normal force is mg. What you will hear me say is, in this situation, it's the same size as mg. And so what I can get away with is putting mg in its place to do the calculation. It's going to be 0.12 times 10 times 9.8. Keegan, what'd you get? I can do this in my head. It's going to be 98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 10.8. I think you're going to go 11.76, I think. 11.76? Yes? Newtons. We're going to, Keegan, keep doing the same thing. It's going to be mu, I don't know the normal force. And I can't really say, oh, but look, I don't know the force the same size as the normal force, but I do know how to calculate the normal force. Apparently the normal force is the same as what? In brackets, mg plus 15. And so it's going to be, what's mu? I don't know, what's mu with you? 0.12, and then it's going to be 10 times 9.8 plus 15. Try that on your calculator, Keegan. Oh, I can do this in my head too. 10 times 9.8 is 98 plus 15. It's going to be 108. It's going to be 113. 113 times 0.12. It's going to be 11.3 plus 2.26. So it's going to be 13.56, I think. Yeah? So you got Keegan? Are you lying? You haven't typed it yet. So, did you? Oh, I stand corrected. And that's a force, newtons. Okay. Well done, my friend. Hey, Jan, what does C want me to do? I think this is my winner minus loser because I'm pretty sure the first diagram is accelerating horizontally. So look at the first picture. Who's winning? I don't think they are. Which way do you think we're accelerating in picture A? In the left-hand picture. I think so. Now, we'll find out if we've guessed wrong if when we solve for A it's negative, then the acceleration is in the opposite direction. But for now, Jan, I think I would go winner. Who's the loser? Equals what? No. Winner minus loser equals. Yes, good. We're brushing the cobwebs off. I know, you were first semester last year too. What about in the second situation? Who's winning? Probably. Who's losing? Equals. Oh, Mr. Dewick, it's the same equation. Am I going to get the same answer? No, because the parameters are going to be different. But it's the same tug of war between the same two forces. Friction and F applied are having the tug of war. Francesco, what does D want me to find? Oh, how would I get the A by itself? I'll move the M over. Yeah, I'm going to, and you know what I'm probably going to do? Because I'm lazy, I'm going to go chunk, chunk, and now I can go straight to numbers. A equals, Francesca, what was F applied? Was it 20? Yeah. Minus 11.76 divided by 10. Oh, that dividing by 10, I can do that in my head. It's going to be 11.76. It's going to be 20, take away 11, it's going to be 9, take away 8.23, 0.84. 0.824? Or am I wrong? Yeah. Jan, is that a big acceleration? Not really. I'm a little worried that we might get a negative answer, but easy fix. Then it's going to be friction minus F applied equals MA. I just picked the wrong winner. So it's a pretty easy fix. It's not something I lose sleep over. It's going to be, again, divide by M. So A is going to be 20 minus 13.56 divided by 10. 20 take away 13 is 7, take away 6.5. 6.44. Oh, still positive acceleration, I think. So it is winning. Is it 0.644? That was dividing by 10. That one wasn't too impressive. Right? Even you could have done that, right? Okay. There can be friction on an object even when it's at rest, because those microscopic hills and valleys will lock up. In fact, they'll lock up a little bit stronger than when you start to slide it. You may have noticed if you're pushing something heavy or if you're sliding something heavy like furniture, getting it moving requires you to push harder than you do keeping it moving. And that's because technically there's two types of μ's. There's two types of coefficients of friction. There's one called static friction and there's one called kinetic friction. So here's our thought puzzle. It says this. If we pull on a desk with a force of 2 newtons and the desk does not move, which of the following is true? A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. You know what? Once again, I think we're going to vote. How high you hold your hand up is how sure you are of the answer. So if we pull on a desk with 2 newtons and the desk does not move, which of those statements is correct? Who says, Mr. Dewick, it's obviously A. Friction is bigger. That's why the desk isn't moving. A. It's got to be A. A. Really? This is interesting. Who says, no, B. Static friction is exactly 2 newtons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You going A? Yeah. Any C? Any D? Okay. Why must A be wrong? Okay, so I'm going to pause the video for a second. So, Francesco, how do I know the correct answer has to be B? Because the object was not, I'm looking for a word that starts letter A. So if it's not accelerating, that means the forces must be, I'm looking for a word that starts letter B. Okay? Which one of Newton's laws did I use in order to prove that? Which is the one that says if we're not accelerating, that means the forces must be balanced? Prepare yourself. I gave you warning.
I remember none of them. I'm going to say 2.
Okay. So, because sadly we didn't know which one. Now, if you know that's Newton's first, for sure, you can write Newton's first. Otherwise, again, we would say this. Since A equals 0, forces must be balanced. And again, I would take that. And you're right. I didn't tell you to memorize them last year. I thought by now you'd reach your laziness point where you might just decide to because you're sick of writing out the explanations. But it's up to you. You said Newton's second. What is Newton's second? Sarah, what's Newton's second? I think you were right. I have no idea. Oh, you don't know? Okay. What's Newton's second? It's the equation. F equals what? MA. I don't like the order that we do, but that's just kind of how physics textbooks always do it. Because to me, F equals MA having 3 variables, I would have made that the third one because that would have given me a stupid way to remember that. Forces come in pairs. That would be a dumb way to remember that it was the second one, but we're stuck with what we got. So static friction then varies from 0 when we're not pushing on the object at all. So is there friction on my table right now? I'm not pushing on it, so there is no force of friction. Now I'm pushing on it towards Quinn with about 10 newtons. Friction is 10 newtons big. I could overcome the force of friction. I'm not going to. Static friction varies from a minimum of 0 when there's no force to cancel out, up to a maximum. And what's the maximum? Static mu times the normal force. That's the biggest it can be. Once it starts to slide, and now I'm being technical, Keegan, you going to make it? You looking awake? Okay? Lose the hoodie on the head if you're getting tired because you're trapping heat. Just a little advice for both of you in the back row there. It does help you stay awake not to put a hat on. If we start it moving, what happens is this value here is smaller than when it's at rest. And that's why once I start it moving, I don't have to push as hard to keep it moving. So I use static mu when it's at rest. I use kinetic mu when it's moving. If the question only gives me one coefficient of friction, Madison, assume it works for both. And for the rest of the unit, we're going to assume they work for both. But today, since we're really diving into friction, let's look at this. It says this. A 5 kilogram object sits on a surface with a static coefficient of friction of 0.3 and a kinetic coefficient of friction of 0.25. In other words, saying that once it starts to move, use that in your friction calculations. But before it starts to move, use this in your friction calculations. It says determine the force required to move the object. You know what? This is a job for a free body diagram. I'm going to do my free body diagram kind of right here because I think I'm going to need some room. So there's my free body diagram. Okay. Kara, what are the forces acting on it? Get the obvious one. You got this. What's the obvious one? I know, I caught you zoning out. Sorry. What's the obvious one? mg, right? So let's do that. Oh, too far. Good. Good. Sienna, is it sinking to the ground like quicksand? Is it flying through like Superman? No. So that means vertically the forces must be, I'm looking for where that starts the letter B, Madison. So which force is pointing at the normal force, same size as mg? And again, freehand eyeball it. Don't be sloppy though and do like a slanty force because we're going to be talking about angles in the next couple of days. And, don't do that. But eyeball it. As long as you're pretty close, you should be okay. Good. What else do we have? Well, now I'm going to imagine a little bit. It says determine the force required to move the object. I'm going to call that F applied. And here, friction. And I drew them matched because part A said determine the force required to get it moving. In other words, how hard do you need to pull just to get it to move? It's when they exactly match at their maximum. So, which force is it asking me to find? F applied. I don't know F applied. Oh, but look at my free body diagram. Which force will F applied be the same size as if it hasn't started accelerating yet? Friction. And so, I'm going to figure out F applied by figuring out the maximum friction. And what's the maximum friction going to be? That's going to be mu static times the normal force. In fact, mu static, I think I even wrote max. That's the hardest I have to pull to dislodge this thing and get it to slide. Maddie, how big is mu static? I don't know the normal force. Oh, but look. I know another force the same size as a normal force. Which one? And so I can go 5 times 9.8. To get this thing to start to move, how hard do I need to pull? Maddie, my angel. 14.7? Okay. What if I'm pulling less than 14.7? What'll happen? Nothing. Okay. So, A. Let's look at B. Let's look at B. Gaia, how hard are we pulling in part B? How big do we have to pull to get this to move in the first place? So, what will the acceleration be exactly as a number then? 0. Not moving. Oh, and how big is friction exactly as a number if I'm pulling with 10 newtons and it's not accelerating? Don't say 14.7. How big must it be exactly? Got to be 10, right? So A says find the B says find the acceleration. It's 0. And find the force of friction. It's exactly 10. If it was any more or any less, it would have to be accelerating. Is that okay, Alice? Good. Alice, how hard are we pulling in part C? How hard are we pulling in part C? How many newtons? I think you're right, couldn't you? 20. Good. Will it accelerate now? Yes. Because now we're definitely bigger than what was holding us at rest. Okay, so now things are going to change. Now, can you just imagine that this arrow is longer? We're not going to redo the free body diagram, but just imagine that it's bigger. Who's winning? Who's winning? Who's losing? Equals ma. We now have a new equation that's going to be F applied minus friction equals ma. Now, they want me to find the force of friction. Okay. Alice, friction is what times what? It's mu times the normal force. But now we're starting to slide, so we're going to use the kinetic, we're going to use the 0.25, not the 0.3, because we started to slide, you don't need to pull as hard. So over here, I'm just going to say friction equals mu k times the normal force. It's going to be 0.3 times, 0.25, Mr. Dewick. Times, I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. It's got to be the same size as mg, which is 5 times 9.8. How big is that, Alice? 0.25 times 5 times 9.8. I should be able to do that in my head. 5 times 9.8 is going to be 49. So it's 49 divided by 4, Mr. Dewick. That's going to be 10, and it's going to be, is it 12.25? Yeah? Okay. Let's walk that over to here. They want me to find the acceleration. Alice, how would I get the A by itself? How would I move this M over? Yep. And to show my work, what I usually just do, if you just cross out the M and do that, that's enough for me to see that you have rewritten the equation. You don't need to rewrite it completely if you don't want to. I'm good with that. Let's start plugging in numbers. F applied was what? 20? Friction was 12.25. And M was 5. Probably do that in my head. 20 take away 12 is 8. Take away 0.25 is going to be 7.75 divided by 5. I could divide by 10 and double it. So it's going to be 0.775. It's going to be 1.4. It's going to be 1.5. It's going to be... Is it 1.525? Or did I carried a 1 wrong? I'm off. What is it?
1.55.
1.55. Golly, Dewick. Should be able to do that. Okay. So I've done, Mallory, this little rant on 2 different Mus, and there's a couple like that in the homework, but then starting for the rest of the unit tomorrow, if you see a Mu, you can assume that it's both static and kinetic. You can use it in both. I'm not going to be that fussy. But I do like to explain why it is that once you get something sliding, you don't have to push as hard. All right. What's your homework? Number 1. 2 is good. 3 is good. 4 is good. 5 is good. 6 is good. 7 is good, but you can skip 8. Yeah, 9. 10 is good, but you can skip 11. 12 is good. You can skip 13. You can 14 is good. Skip 15. 16 is good. Skip 17. That's a fair bit. Did you want to go over the... Hang on, Mr. Dewick. Let's pause the video. Sorry?